So we have reaction mechanisms. Mechanism is a series of steps that would add up to some reaction and tell you something about a step that's going to determine how fast a reaction takes place. So reaction order is determined by experiment. So somebody goes into the lab, they vary the concentration of one reactant, they vary the concentration of the other reactant, and they figure out what the order is of each reactant. Okay, that's first. Then mechanisms are proposed, right? So order is determined by experiment. Here's a reaction. NO2 plus carbon monoxide yields NO and CO2. All right, we've got two reactants. So an experimenter goes into the laboratory and deals with these two gases, and they vary the concentration of this one, they vary the concentration of this one, and they find out, okay, which one has, do they both have the same effect on the rate? Is it first order and first order? Is it second order and first order? What is it? You can't tell just by looking at a reaction what the rate law would be. So you have to do that by experiment. You figure out the order by experiment. Then, after you figure out the order, then you say, okay, based on this, I know this is the order, then this is a possible mechanism, or this is a possible mechanism. And there can be multiple correct answers. Mechanisms usually include multiple steps. So if you went into the laboratory and you found that this reaction was first order with respect to NO2, and first order with respect to CO, then just that reaction could make sense. This reaction makes perfect sense, because what that tells you is that if you increase the number of these molecules, more collisions happen and the rate goes up. And if you increase the concentration of these molecules, more collisions happen and the rate goes up. So first order and first order, you wouldn't need a mechanism, a long mechanism. It would just be like, okay, maybe that's the mechanism. They bump it, these molecules, they collide, exchange an oxygen, go about their business. But usually you're looking at multiple steps. I only have 2 steps here, but you can have reaction mechanisms with 5 steps, 4 steps, whatever. So slow step is the one that is rate determining. So if it's only 1 step, then you wouldn't be worried about it. But if you have multiple steps, you want to know something about the slow step, and you want to know how to work this. So I've drawn up here 2 scenarios, scenario A, scenario B. We've got A, where the slow step would be the first step, and scenario B, where the slow step is the second step. And we'll look at those. So here are some rate laws, right? These are some rate laws that could be for this reaction. So the rate law could be equal to some rate constant times the concentration of NO2 times the concentration of CO, right? First order with respect to NO2 and CO, and that would make sense if it was just this. If the reaction was a 1-step reaction, 1 elementary step, boom, a bimolecular collision, they collide, they're done. So that would make sense for the first one. Then we have rate equal to NO2 squared CO, or rate equal to a rate constant times the NO2 squared. That would be second order with respect to NO2, and carbon monoxide doesn't even affect the rate. So both of these two are possible, and let's look at why. So slow step is rate determining. So for scenario A, the slow step is step 1. So this one just happens so fast. As soon as, so we've got NO2 colliding with NO2, a bimolecular collision, and we get NO and NO3, but as soon as the NO3 gets made, it reacts with CO and gives us CO2 and another NO2 molecule. So yeah, this one's fast, this one's slow. So as far as our matching rate laws with a reaction mechanism, only the first step here is going to matter. And so we would look at this. We say, okay, well, what would the rate of this reaction be if just step 1 was there? And the rate equal to some constant times the concentration of NO2. But it's not 1 molecule of NO2 breaking apart, right? These are 2 NO2 molecules colliding. So if I double the concentration of NO2, then this part of the reaction is doubled and this part of the reaction is doubled. So actually this would be second order with respect to NO2. So since this is the slow step, that's what the rate law would look like for this scenario. And carbon monoxide, changing the carbon monoxide concentration would not affect the rate, because it's how fast the NO2 molecules collide with each other, producing the NO3, that determine the rate. All right, so you see this last one, K, rate equals K times the concentration of NO2 squared. That makes sense if the first step that I've written here is the slow step. B, so we got reaction B. Oh, let me pause for a second. We've got these two steps, and the two steps, if we look at the reactants and products, you notice there's NO2 here, there's 1 mole, and it looks like, maybe it looks to you like there's 2 moles. Well, on the product side, there's another one, right? So that would cancel, and that would cancel, and that would cancel, and that would cancel. So NO3 is our intermediate in this reaction. If you add these two steps together, they add up to the reaction overall. That needs to be true for any reaction mechanism. Has to add up to the overall reaction. All right, let's get to scenario B. So scenario B, we've got NO2 and NO2, again colliding, but that's fast. That happens very, very quickly, and then NO3 and CO combine, or collide. So this is our slow step. Well, what is the rate of step number 2? That'd be like, oh, rate, I'll do sub 2. It would look like that, right? It depends on the concentration of carbon monoxide and the concentration of NO3. And the greater the concentration of each of these, the more collisions take place. The more collisions take place, the higher the rate would be. There's a problem, though. You can't write an intermediate in a rate law, because when you go into the lab and you do an experiment, you can't increase the concentration of an intermediate. You can increase the concentration of a reactant. So your rate laws have to include only reactants, occasionally products if it inhibits a reaction. So let's look at where this NO3 comes from. Right? The production of NO3 is going to depend on that first reaction. Right? We need a collision between NO2, a collision between NO2. They collide and they produce the NO3. So that has NO2 as second order, just like it did before. So to get this NO3, we need these two things to collide. So what we're going to do is substitute that in here, and we would end up with that rate overall. These K's are rate constants. Anytime rate constants are combined, it might be a different value, but they kind of get absorbed together. It's a constant. So the rate is going to depend on some rate constant and the concentration of CO and the concentration of NO2 squared. Those are reaction mechanisms. Slow step determines the rate. Don't write intermediates in